Alright, now we're going to figure out the properties of the trig functions, beginning with the domain and range, and we're going to start with the sine function as a consequence of that, the cosecant function. Alright, for sine of x, the domain, if you notice it keeps going on and on, so the domain would be all real numbers, or just a set of numbers from negative infinity to infinity. And the range, you notice it never goes between -1 and +1. So, but it does include those points, so you could say it's all the numbers from -1 to +1, including the brackets. Now I'm going to show you how to create the cosecant function from sine. Remember, cosecant of x, remember that's equal to 1 over the sine of x. So what you do is you take all these points here, all these little minimum and maximum values of the sine function, and you can draw the branches of the cosecant function. And see where sine of x is 0? That would be where cosecant is undefined, so you could draw your asymptotes for the cosecant function everywhere sine is 0. For cosecant, looks like the domain would be all real numbers except for the asymptotes. So it would be the set of all x values, such that x cannot equal numbers such as pi, 2 pi, etc. So you could say x cannot equal some number times pi, with k being an integer. Because as long as it's an integer, there will be an asymptote at that number. And the range, looks like it keeps going upward from +1 and then downward from -1. So it'd be -1 is greater than or equal to y, and y is less than or equal to +1. If it goes downward from -1, yes, because -1 would be greater. Making sure I had the inequality symbols correct. So that would be the range. So now let's move on to cosecant and, as a consequence, the secant function. So now for cosine of x. Let's figure out the domain and range. If you notice, it keeps going on and on forever. So the domain would be all real numbers, or the interval from -infinity to +infinity. And the range, like the sine, it just goes from -1 to +1, but it does include the endpoints, so you'd use brackets. Now, the cosecant function, remember that's just, rather the secant function, secant, remember it's 1 over the cosine. So you draw that graph the same way. You can draw your asymptotes where, remember, where cosine is 0, that would make secant 1 over 0, so secant would be undefined where cosine is 0. So everywhere cosine crosses the x-axis, you can draw your asymptotes. So now the domain would be for the domain for secant would be the set of all x's such that x cannot be one of these odd multiples of pi over 2, like 1 pi over 2, 3 pi over 2, 5 pi over 2, etc., etc. So you could say it's the set of all x's such that x cannot be k pi over 2, with k being an odd integer. And the range, it's the same as the cosecant, set of all y values such that -1 is greater than or equal to y, because we want all the y values that are less than -1. But wait, it should be all the y values that are actually greater than +1, because like +2, +3. I don't know why I just wrote 3 there. So it should be +1. So this symbol should be the same on the previous slide, so if I wrote it wrong, go back and change it in your notes. Now, for tangent, remember tangent is equal to sine over cosine. So, remember anywhere where cosine is 0, that would make the tangent undefined, so that's why we have asymptotes everywhere cosine is 0. So at the odd intervals of, at the odd multiples of pi over 2. Now the domain, notice each branch of the tangent function keeps going on for infinity in both the positive and negative y directions, but not in the x directions, because we have the asymptotes where the cosine would be 0. So the domain, since cosine cannot be 0, it'd be the same domain as the secant function, so it'd be set of all x values such that x cannot be k pi over 2, with k being odd. And the range, since it keeps going onward forever in the positive and negative y directions, you actually could just write it as an interval, the range being from negative infinity to infinity. The last of the 6 trig functions we're going to learn about is what we call the cotangent function. Remember, alright, here's the graph for cotangent. Remember, cotangent is just cosine over sine. Make this a little bit smaller so I can have a little bit more room to write. Alright, you notice there are asymptotes where the sign would be 0. So at intervals of pi and negative pi. Or intervals of pi, where the number in front of pi is an integer. Like 0 pi, 1 pi, 2 pi, 3 pi, etc. So the domain for cotangent would be the set of all x values such that x cannot contain k pi, with k being an integer. And the range, you notice it keeps going on and on forever in both the positive and negative y direction, so the range would be from negative infinity to positive infinity. Alright, now we'll go over how to determine the period of trig functions. Remember, the period is just how far you have to go on the x-axis till the trig function starts repeating itself. I'm going to illustrate what it is, the concept of the period, with the sine function. Now, if you look at the sine function, say pick a point on the sine along the graph, say just pick where it crosses the x-axis, and if you notice you have to go a distance of 2 pi before it crosses again, and then it just keeps going on and on and on. Or you have to go 2 pi before it crosses again while going upward. So if you notice, the period would just be 2 pi. Likewise, if I want to illustrate this with the tangent graph, Notice for the tangent function, you start at 0. If you start at 0 like this, figure out where this branch is located along the x-axis. If you go to an identical point, you only have to go pi units over. So the period for tangent is not 2 pi, but just pi. Because that's the point where the graph starts over. Likewise, for cotangent, the period would just be pi. Alright, so let me give you a formal definition for what we call a periodic function. Alright, a function is called periodic if there's some positive number p such that whenever your angle is in the domain, if you add that period to the angle, your output is just equal to the original angle, whenever you just put the original angle in. The smallest number p is what we call the fundamental period. And that's where we're talking about how the fundamental period of sine is 2 pi. Fundamental period of tangent is pi. So now here are the periods for the 6 trig functions. Alright, what this means is that if you go 2 pi units over on the sine function, you'll get to a point where the graph starts over. Likewise for cosine, if you go 2 pi units over, you'll go to where the graph starts over. We establish that the period for tangent is pi, because if you go to pi units over, you'll go to an identical point on the graph. Likewise for cotangent. Okay, so here's a 3-part example. It says find the exact value of, let's start with sine of 17 pi over 4. Now, this can be broken down into, say, 16 pi over 4 plus pi over 4, which would be 16 pi over 4 is the sine of 4 pi plus pi over 4. Remember, 4 pi is just 2 periods. Remember, we said the period of sine was 2 pi, and 4 pi is just 2 of those, plus pi over 4. Since this is just 2 periods, the 2 times 2 pi, that's equivalent to sine of pi over 4 by the definition of a periodic function, and sine of pi over 4 is just square root of 2 over 2. Now let me erase that so I can have room to write part B on. So, cosine of 5 pi. That would just be cosine of 4 pi plus pi. Cosine of 4 pi is just 2 periods, so that's just equal to cosine of pi. Cosine of pi is just negative 1. Alright, so let me erase that. And these values we're getting for like sine of pi over 4 and cosine of pi, that's just from the unit circle that we've gone over. So tangent of 5 pi over 4. Remember, that's equal to just tangent of 4 pi over 4 plus pi over 4, because 4 pi plus pi is 5 pi. 4 pi over 4 is the same as pi plus pi over 4. Since pi is our period, that's the equivalent to tangent of pi over 4. Tangent, remember, is equal to sine over cosine, so sine of pi over 4 divided by cosine of pi over 4. So that's equal to square root of 2 over 2 divided by square root of 2 over 2, which is just 1. Now we're going to go over how to determine the signs of the trig functions in a given quadrant. Remember, we said in a previous video that on the unit circle, sine is equal to y, cosine is equal to x, tangent is y over x, cosecant is 1 over y, secant is 1 over x, and cotangent is x over y. So, So if you look at the first quadrant, both the x and y are positive. So that means all 6 trig functions will be positive. In the second quadrant, well, let's label them too. In the second quadrant, x is negative, y is positive. So, since y is positive, sine would still be positive, cosine would be negative. Since they're different signs, tangent would be negative, so would cotangent. Cosecant would still be positive, and secant would be negative. The third quadrant, they're both negative, x and y's. So sine would be negative, cosine would be negative. Tangent, since you're dividing a negative by a negative, I don't know why I wrote -1, it should just be negative. Tangent would be positive. Likewise, secant and cosecant would be negative, and cotangent would be positive. Alright, and in the fourth quadrant, x is positive, y is negative, so sine is negative, cosine is positive, which means tangent would be negative, cosecant would be negative, secant would be positive, and cotangent, since you're dividing things that have opposite signs, it'd be negative. So here's an example. If sine is less than 0 and cosine is also less than 0, name the quadrant in which the angle lies. Alright, if sine is less than 0, that means y is negative, and if cosine is less than 0, that means x is negative. The quadrant in which both values are negative would be quadrant 3. We're going to restate some identities, beginning with the quotient identities. Remember, tangent is equal to sine over cosine. Cotangent is equal to cosine over sine, in case you don't have that written down 400 times already. Next, we're going to restate the reciprocal identities. Alright. Remember, reciprocal identities just say that cosecant is equal to 1 over sine. Likewise, sine is equal to 1 over cosecant. Secant is equal to 1 over cosine. Likewise, cosine is equal to 1 over the secant. And cotangent is also equal to 1 over the tangent. And tangent is equal to 1 over the cotangent. The next thing we're going to talk about is what we call the Pythagorean identities. Alright. From this, you may remember the equation for a unit circle. It's just x squared plus y squared is equal to 1 because it's centered at the origin and has a radius of 1. Remember, x is equal to cosine, so instead of writing x squared, you could write cosine squared. Instead of y squared, you could write sine squared. So you may remember this identity, cosine squared plus sine squared is equal to 1. You may see it written as sine squared plus cosine squared is equal to 1. They mean the same thing, so just remember this. Alright. So now, if we take that identity, sine squared plus cosine squared, and we divide it by cosine squared, divide everything by cosine squared, sine squared over cosine squared gives you tangent squared. Cosine squared divided by cosine squared gives you 1, and 1 over cosine squared gives you secant squared. You need to remember this as well. Likewise, if we take that same identity, sine squared plus cosine squared equals 1, and divide it by sine squared, those cancel out, so you're left with 1, and then cosine squared over sine squared gives you cotangent squared. And 1 over sine squared gives you cosecant squared of x. So, if you've taken trig before, you might remember these. You will need to remember them again for this class. Now let's do some problems where we work with those identities. Alright, so here's an example. Given sine is equal to square root of 5 over 5, cosine is equal to 2 square roots of 5 over 5. Find the values of the 4 remaining trig functions using identities. Alright, so we can start with tangent. It's equal to sine over cosine. So it's equal to square root of 5 over 5 divided by 2 square roots of 5 over 5. We can cancel out the square root of 5 over 5, so that would just leave us with 1 on top and 2 on bottom, so it'd just be 1/2. Now secant, you get by flipping the cosine, so it'd be 5 over 2 square roots of 5. But we don't like having a radical on the bottom, so we can multiply by square root of 5 over 5, or square root of 5 over square root of 5. So that would be 5 times square root of 5 on top. And then square root of 5 times square root of 5 is just 5 times 2 gives you 10. 5 and 10 reduced to 2. So it'd be square root of 5 over 2. Cosecant, it's just 1 over the sine, so you flip the sine function, so it's 5 over square root of 5. Follow the same process, multiply by square root of 5 over square root of 5. So on the numerator you would have 5 times the square root of 5. And then on the denominator you'd have square root of 5 times square root of 5, which is just 5. The 5's cancel out, so you're just left with square root of 5. And for cotangent, that's just, remember, 1 over the tangent. So it'd just be 2 over 1, because you flipped the tangent, which is just 2. And so here's another example, a two-part example. It says find the exact value of each expression without using a calculator. So, for part A, tangent of 20 degrees minus sine of 20 over cosine of 20. Right, you know sine over cosine gives you tangent, so that would just be tangent of 20 degrees. So tangent of 20 degrees minus tangent of 20 degrees just gives you 0. Now for part B. No. We know secant is 1 over the cosine. Likewise, cosine is 1 over the secant. So 1 over secant squared would be cosine squared of pi over 12. And then sine squared of pi over 12 plus cosine squared of pi over 12. We have sine squared plus cosine squared, which gives us 1. Alright, I do want to remind you of something. Sometimes you'll be given problems for points that are on a circle, but not necessarily on the unit circle. If a point is on a circle, but not the unit circle, remember sine is y over r, because remember on the unit circle, the radius is 1, so that's why the sine is y. That's why we say the sine is y, because on the unit circle we get y over 1 for the sine value. So, our sine is just y over r. Cosine is just x over the radius. And tangent is just y over x. So, you notice that would still be y over r divided by x over r, because if you were to do keep change flip, you would have y over r times r over x. So that means tangent is still sine over cosine, even though we're not on the unit circle. Likewise, and the reason we get this is because if you have an angle here, you have the y value, the x value, the angle, and then the radius. Sine is just the opposite over the hypotenuse, so it's just y over r. Cosine is just the adjacent side, which is x, over r. And tangent is just y over x. Or if you want to work it out algebraically, it'd still be sine over cosine. So with that in mind, let's do the following example. So for example 5, given that sine is 1/3 and cosine is less than 0, find the exact value of the remaining 5 trig functions. If cosine is less than 0, that means it's odd. And since tangent is equal to positive 1/3, that means the y is positive. So that means we're in the second quadrant. And since y is 1/3, that means the y value is 1 and the radius is 3. So we need to figure out the x coordinate. So you have x squared plus 1 squared equal to 3 squared, which means x squared is equal to 8, which means x, since x value is negative, it'd be negative square root of 8, which would simplify to negative square root of 4 times 2. Square root of 4 is 2, so move that to the outside, so it's just be negative 2 square roots of 2. So now you can find the values of the other trig functions. Let me erase that so I can have room to write. So cosine, and remember, is equal to x over r, adjacent over hypotenuse, so it's negative 2 square roots of 2 over 3. Tangent is just y over x, so 1 over negative 2 square roots of 2. But we don't like having a radical on the bottom, on the denominator, so multiply by square root of 2 over square root of 2. So that's equal to just square root of 2 on top, and then negative. The square root of 2 times square root of 2 is just 2 times negative 2 would be negative 4. So you could rewrite tangent as just negative square root of 2 over 4. So cosecant of our angle is just equal to, flip the sign, so it's 3 over 1, which is just 3. Cosecant why did I write that twice? Secant, you just flip the cosine, so it'd be 3 over negative 2 square roots of 2. We don't like having a radical, so multiply by square root of 2 over square root of 2, so that'd be negative 3 square roots of 2 over 4. And cotangent, you flip the tangent, so it'd be negative 4 over square root of 2. Multiply by square root of 2 over square root of 2. So that would be negative 4 square roots of 2 over 2, which would be negative 2 square roots of 2. And there are the values of the other 5 trig functions. Alright, now we're going to go over the even and odd trig functions. To remind you, in general about even and odd functions, a function is even if you plug in negative x and you get the same function out. Likewise, a function is odd if you plug in negative x and you get the opposite thing out. Remember, even functions are symmetric about the y-axis. Meaning they're reflections about the y-axis. And odd functions are symmetric about the origin. Now I'm going to illustrate whether cosine and cosine functions are even and odd. I'm going to show you how we determine that by looking at the unit circle. So here's the unit circle. Say if I give you sine of negative x or negative theta, whatever. that means instead of going, say, in this direction, that means you would go in this direction. You go in the negative direction, which would be clockwise. Now, notice, if you go in the negative direction, then sine would go from being positive to negative, so that'd be negative sine of x. So sine is odd. Likewise, if you were to do cosine, cosine is still positive regardless of which direction you go in. So if you go take cosine of positive x, if instead you were to take negative x, go in the negative direction, cosine would still have the same sign. So instead of it being negative cosine of x, it'd just be the same thing because cosine's still positive in both the first and fourth quadrants, so cosine is even. If you want, you can ask me during class about, say, if for any angle greater than 90 degrees, you'd still get the same thing, still the same concept. Sine would still be odd, cosine would still be even. You'd still get the same thing regardless of the size of the angle. So let me put up a chart saying which angles are even, which angles are odd, since I think you get the idea right now. If you notice here, cosine and secant are the only even functions. Everything else is odd. So let's do some examples using the even and odd properties. Sine of negative 45 degrees. Alright, we said sine was odd, so that'd be the same as negative sine of 45 degrees. So that'd just be negative square root of 2 over 2. And for cosine of negative pi, we said cosine was even, so that's just the same as cosine of pi, which is negative 1. Part C, we have cotangent of negative 3 pi over 2. That'd be negative cotangent of 3 pi over 2, which is just negative cosine over sine of 3 pi over 2. Alright, and I believe cosine at 3 pi over 2 is 0, sine is negative 1, so 0 over negative 1 is just 0. Yes, you have the negative sign in front, but negative 0 is still just 0. Likewise, tangent of 37 pi over 4. Negative 37 pi over 4. That's equal to negative tangent of 37 pi over 4. This is when we can use those periodic properties that we learned before, so that's negative tangent of 36 pi over 4 plus pi over 4. We chose this because we know 36 over 4 reduces to 9 pi. Plus pi over 4. Now since the period of tangent is pi, 9 pi just means it started over 9 times, so that's the same as negative tangent of pi over 4. We said in earlier examples the tangent of pi over 4 is 1, but since it's negative, it'd be negative 1.